Namaste students, welcome back to my channel. Students, today in this video we are going to start the properties of the D block element. We'll cover the properties of the D block element in two different videos. Today in this video we'll cover the half of the properties, and in next video we'll cover the next half of the properties. So without any delay, let's get started. First property which we are going to discuss is atomic and ionic radii. Now, the atomic and ionic radii of the D block elements, the atomic radii of the D block element lie in between the S and the P block element. If we talk about the atomic radii, of the D block element, atomic radii of D block element lies in between the S and the P block elements. Now, generally, if we talk about the general trend, generally the atomic radii of the D block elements, decreases with increase in the atomic number, but the decrease in the atomic size is small after midway. What I am saying, that when we move left to right in a period, in any transition series of the D block, with increase in the atomic number, atomic radii decreases, but the decrease in the atomic radii is small after midway. Let us take one example. If I write the first transition series, that is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. This is our first transition series, and if I write the atomic radii of these atoms, these elements in picometer, then the atomic radii is 162 picometer, 147 picometer. Then the atomic radii of vanadium is 134 picometer, 127, then 126, 125, 125, 124, 124 and 138. So what we are observing? We are observing that when we move from scandium to titanium, titanium to vanadium and vanadium to chromium, atomic radii decreases. But after chromium, the decrease in atomic radii become very less. Though there is decrease in atomic radii, but the decrease in atomic radii is very, very less. Now, what is the reason behind this? As we move from left to right in a period, what happened? First thing, atomic number increases. Now, due to the increase in the atomic number, nuclear force of attraction also increases. And because the coming electron is entering in the D subshell, penultimate D subshell, and we know that the shielding effect of D is very poor. So because of all these reasons, atomic radii decreases with increase in the atomic number. But what happened after chromium? Now, in scandium, we have 1 electron in D. In titanium, we have 2 electron in D, 3 electron in D, 5 electron in D, 5 electrons, 6, 7, 8, 9 and 10 electron in D. Means as we move from left to right in a period, what happened? The number of electrons in the D orbital increases. Due to the increase in the number of electrons in the D orbital, their overall shielding power increases. And due to the increase in the overall shielding power, the effect of the increased nuclear charge not dominated as much. Clear? As we move left to right in a period, what happened? The number of electrons in the d orbital, increases. Due to the increase in the number of the d orbitals, the overall shielding power, होगी वो क्या होगी, increase होगी. And that shielding power, क्या करेगी, जो effective nuclear charge का इफेक्ट है, द इफेक्टिव न्यूक्लियर चार्ज, जो इंक्रीज इफेक्टिव न्यूक्लियर चार्ज का इफेक्ट है, उसको क्या कर देगी, कम कर देगी. Means the increased overall shielding effect of the d electrons decreases, suppressed the increased effective nuclear charge, and due to this there is net result in very less decrease in the atomic radii. जिस वजह से आपका atomic radii क्या होगा, decrease, but to a very less extent. So why atomic radii become less decrease after midway? Because after midway, what happened? Due to increase in number of d electrons, what happened? The shielding, the overall shielding power of d orbital increases, which suppressed the effect of nuclear charge. I hope through this line it is clear that why after midway the decrease in atomic radii is very less. So the first information is, when we move left to right in a period, what happened? With increase in the atomic number, atomic radii decreases, but after midway the decrease in atomic radii is very less because of the increased shielding power of the d orbital, which suppress the effect of the increased nuclear charge. But if you observe this series, when we move from copper to zinc, again we get a increase in the atomic radii. But according to this concept, the atomic radii of zinc should be less than that of the copper. Now, what is the reason behind this? The reason behind this is the repulsion in dd electrons. Now, we know that in zinc we have what? 3d10 4s2. The electronic configuration of zinc is 3d10 4s2. Now, due to the maximum number of d electrons, there is a repulsion between the electrons, and that repulsion means from here means from iron. From iron we get pairing in d orbitals, because in iron we have configuration 3d6. So the pairing starts here. From 3d6 to 3d10 we get dd repulsion also. But up to copper the effect of dd repulsion is suppressed. But after copper the dd repulsion becomes overcome. The dd repulsion becomes dominative, and that dd repulsion suppressed the effect of the nuclear charge, as a result of which electron cloud becomes spread. In a larger area, and that's why we get an increase in atomic radii. So जब हम copper to zinc में move करते हैं तो आपका क्या होता है? dd repulsion means the repulsion between the dd electrons. dd repulsion आपका क्या होता है? इंक्रीज हो जाता है, और वो किससे ज्यादा हो जाता है? इफेक्टिव न्यूक्लियर चार्ज से. वो इफेक्टिव न्यूक्लियर चार्ज को सप्रेस कर देता है, एज अ रिजल्ट ऑफ विच इलेक्ट्रॉन क्लाउड ज्यादा एरिया में स्प्रेड हो जाता है और आपका एटॉमिक साइज इंक्रीज हो जाता है. So first atomic size decreases. Why? Because nuclear force of attraction increases. After midway the decrease is very less. Why? Because the increased overall shielding power suppressed the increased nuclear force of attraction. And at the last of the series, there is an increase in the atomic radii due to the DD repulsion. So this is the change in the atomic radii. This is the variation in the atomic radii in the transition series when we move left to right in a transition series. Now we'll talk about the variation of the atomic radii when we move from first transition series to second and second transition series to third. So as we move from first to second transition series and from second to third transition series, what happened? Due to the increase in the number of the shells, atomic radii increases. Obviously, due to the increase in the number of shells, atomic radii increases. Suppose if I talk about zirconium, the second member of the second transition series. If I talk about zirconium, the atomic radii of zirconium is 160 picometer. 160 picometer. If I talk about niobium is the third member of the second transition series. So the atomic radii of niobium is 146. It is 146. So titanium 147, zirconium 160, vanadium 134, niobium 146. So as we move from first to second transition series, due to the increase in the number of the shells, atomic radii increases. This is a simple thing. जब हम down the group आते हैं, shells increase होता है तो size increase होगा. But when we move from second to third transition series, there is a very less increase in the atomic radii, or we can say that there is no increase in the atomic radii. लेकिन जब हम सेकेंड से थर्ड ट्रांजिशन सीरीज में आते हैं तो या तो वहां पे बहुत कम इंक्रीज होता है या फिर बिल्कुल भी इंक्रीज नहीं होता है. For example, if I talk about the second member of the third transition series, that is hafnium. Hafnium, its atomic radii is 158 picometer. It's 158 picometer, means less than zirconium. And if I talk about the next member, that is tantalum, it is 146, means neither increase nor decrease. The atomic radii of hafnium is 158 and the atomic radii of tantalum is 146. Now, when we move from first to second transition series, due to the increase in the number of shells, atomic radii increases. Obvious thing it is. It is obvious thing. But when we move from second to third transition series, what happened? That there is either very little increase in the atomic radii or not at all increase in the atomic radii. The reason is lengthenoid contraction. The reason is lengthenoid contraction. Lengthenoid contraction. Now, what is lengthenoid contraction? We know that the first member of third transition series is lanthanum. We know that. After lanthanum, we know that we get F block elements. Lanthanum के बाद हमें F block elements मिलता है. F block completely fill होता है. Then फिर आपका hafnium fill होता है. Clear? It means in between lanthanum and hafnium we have F orbital also. And we know that the shielding effect of F orbital, is very, very poor. Is very, very poor. जो shielding effect होती है F orbital के electrons की वो बहुत poor होती है. Now, when we are moving from zirconium to hafnium, means from second transition series to third transition series, what happened? Atomic number increases. Due to the increase in the atomic number, nuclear force of attraction increases. Nuclear force of attraction increases as well as the shielding effect. Due to the involvement of the F electron, the shielding effect becomes very, very, very poor. As a result of very poor shielding effect, the increased nuclear charge dominates, and that increased nuclear charge results in a very less increase in the atomic radii. So I hope this is clear to you. That is why the atomic radii remains same when we move from second to third transition series. The reason is lanthanoid contraction. And what is lanthanoid contraction? Due to the involvement of the f electrons, the effect of the nuclear force of attraction dominates over the shielding effect, as a result of which there is net decrease in the atomic radii, net contraction in the atomic radii, and that contraction is known as lanthanoid contraction. उसे हम क्या कहते हैं? Lanthanoid contraction कहते हैं, क्योंकि lengthenoid, why? Because it is coming after lengthenum. So lengthenum के बाद आ रहा है, that's why lanthenoids. और उनके आने की वजह से atomic radii increase होने की जगह decrease होता है, contract होता है, squeeze होता है. That's why it is lanthanoid contraction. So when we move from first to second transition series, there is no role of f orbital electrons, so there is increase in atomic radii. And when we move from second to third transition series, we have f electron. That's why there is either very little increase or no increase or even decrease in the atomic radii. So this is all about the atomic radii, that when we move left to right in a period, what happens? First atomic radii decreases up to half of the series, and after that the decrease is very less due to the increased shielding power of the overall d electrons. At the last of the series, there is again increase in the atomic radii due to the dd repulsions. And when we move up to down from first to second, no change, there is an increase in atomic radii. But when we move from second to third, due to the involvement of the f electrons के involvement की वजह से size क्या होता है? Increase नहीं हो पाता है. That is known as lanthanoid contraction. If we talk about ionic radii, the ionic radii shows the same change as shown by the atomic radii. Means when we move left to right in a period, what happens? Ionic radii decreases, but the decrease in the ionic radii becomes less after midway. But if we compare the ionic radii of the d block elements with the s and the p block. So if we talk about a particular transition series, if we talk about a particular period, the ionic radii of d block element are always less than the ionic radii of the s and the p block element. Clear? आयनिक रेडियाई जो डी ब्लॉक एलिमेंट्स का होगा वो एस और पी ब्लॉक एलिमेंट से हमेशा छोटा होगा. दिस वी हैव नॉट टोल्ड इन atomic radii. In atomic radii, we studied that the atomic radii of d block element lies in between s and p block. But ionic radii के लिए मैं कह रही हूँ that the ionic radii of d block element are smaller than the s and the p block element. Now what is the reason behind this? In s block we have metals, in p block we have non-metals. It means in p block the maximum chance of getting is anion, and in s block we get cation, and because d blocks are metals, so we get cation. So when we are moving left to right in a period, what happens? Atomic radii decreases. So obviously the atomic radii of d block is less than that of the s block, and if atomic radii is less, then the ionic radii of d block should be less than that of the s block. But if we talk about the p block, in p block we get anion. And we know that the anion size is greater than the cationic size, because we are talking about a period. हम एक period की बात कर रहे हैं. Suppose if I am talking about this period, so इस period में इसके बाद जो p block आएंगे उनका ionic radii इनसे बड़ा होगा, और इससे पहले जो s block आएंगे उनका ionic radii भी इससे बड़ा होगा. Clear? It means the ionic radii of the d block element are less than the s block as well as the p block, because in s block we are getting cation and in p block we are getting anion. That's why the ionic radii of the d block are smaller than that of the s block and the p block. So this is all about the atomic and the ionic radii of the d block elements. Now we will talk about the metallic characters of the d block elements. Second is metallic character. metallic character. Now, except mercury, all other elements of the D block shows typical metallic character. Except mercury, all the elements of the D block shows typical metallic character. For example, they are hard, they have luster, they are malleable and ductile, they have high melting point and boiling point, they have high tensile strength, So except mercury, all other elements of the D block shows typical metallic character. Now, what is the reason behind this? The reason behind this is, we know that in D block elements, the electrons are present in the penultimate D subshell. Now, because the ionization enthalpy of transition element is very less, the ionization enthalpy of transition element is less. Now, due to less ionization enthalpy, due to low ionization enthalpy, what happen? They can easily forms metallic bond. Due to low ionization enthalpy, they can easily forms metallic bond. And that's why they shows typical metallic characters. Clear? आपके जो D block elements हैं, D block elements की जो ionization enthalpy होती है वो कम होती है. Ionization enthalpy कम होने की वजह से वो क्या बनाते हैं? Metallic bond, and due to the formation of the metallic bond, they have metallic characteristics in them. Now, the strength of the metallic bond depends upon the number of the unpaired electrons. How? More the number of the unpaired electron, more the number of the metallic bonds, and more the number of the metallic bond means greater the bond strength. Greater the bond strength means more metallic the element. So the strength of the metallic bond depends on the number of unpaired electrons. And if we have more number of unpaired electrons, then we get greater number of metallic bonds. And if we get greater number of metallic bonds, it means the element is more metallic in nature. And because of this reason, if we talk about the middle members of the first, second and third transition series, which are chromium, molybdenum and tungsten. If we talk about these members of first, second and third transition series, because of very large number of unpaired electrons, because of maximum number of unpaired electrons, they are very hard metals in their transition series. Clear? इनमें सबसे ज्यादा हमारे क्या प्रेजेंट होते हैं? अनपेयर्ड इलेक्ट्रॉन्स प्रेजेंट होते हैं अपने पीरियड्स में. दैट्स व्हाई ये क्या होते हैं? वेरी हार्ड मेटल्स इन देयर पीरियड. But if I talk about zinc, cadmium and mercury, they have no unpaired electrons. And because of the absence of the unpaired electrons, they are soft metals. So the metallic character, the metallic character depends on the metallic bond. The strength of the metallic bond depends on the number of unpaired electrons. More the number of unpaired electron, greater is the metallic strength, and greater is the metallic strength means more is the metallic character, and that's why we get very hard metals. But if we have less unpaired electron or no unpaired electron, then the metallic strength is also less, and if metallic strength is less, then we get soft metals. So this is about the metallic characters of the D block elements. Now we'll talk about the melting point and the boiling point of the d block elements. Third is melting and boiling point. Third is melting and boiling point. Now, in our previous point, we have studied that they show typical metallic character, and if they have metallic character, it means they show high melting and boiling point. So transition metals have high melting and boiling point, but the melting and the boiling point increases, first increases and then decreases. Means when we move left to right in any transition series, the melting and boiling point first increases and then decreases. It means when we move from scandium, titanium, vanadium, chromium, then up to chromium, we get an increase in melting point. Then in manganese, we get a sudden decrease. Then after manganese, we get a little bit increase and then decrease. So it means if we talk about general, so melting point first increases and then decreases. Clear? First point, the melting and boiling point of these elements are high because they show metallic character. Second thing, melting and boiling point first increases and then decreases. First increases and then decreases. Now what is the reason behind this? The melting and boiling point strength depends on the number of unpaired electrons. Again, the melting and boiling point strength depends on the number of unpaired electrons. Now, when we move left to right in a period, what happens? First, number of unpaired electrons increases and then decreases. So that's why first melting point increases and then decreases. Clear? But in manganese, we talk about manganese and technetium. If we talk about manganese and technetium, there is an abnormal decrease in the melting and boiling point of manganese and technetium. Means आपका scandium, titanium, vanadium, chromium, manganese, then iron. It means the melting and boiling point of iron should be lower than that of the manganese. Iron का melting and boiling point manganese से कम होना चाहिए, because in manganese we have 5 unpaired electron and in iron we have 4 unpaired electron. तो number of unpaired electron तो ज़्यादा है manganese में. It means the melting and boiling point of manganese should be greater than that of the iron, but it is less than that of the iron. So what is the reason behind this? The reason behind this is stable configuration. Very stable configuration. In both of these, we have D5S2 configuration. We have D5 and S2 configuration, means highly stable configuration. And because of highly stable configuration, these elements do not show delocalization of electron, and if they do not show delocalization of electron, then there is very less tendency to form the metallic bond. Clear? बहुत ज़्यादा स्टेबल कॉन्फ़िगरेशन होने की वजह से ये क्या करते हैं, इलेक्ट्रॉन के डीलोकलाइजेशन को शो नहीं कर पाते हैं, एंड बिकॉज ये इलेक्ट्रॉन्स को डीलोकलाइज नहीं करते हैं, अपनी स्टेबिलिटी को मेंटेन रखते हैं, इसलिए ये मेटालिक बॉन्ड की फॉर्मेशन भी नहीं कर पाते हैं, एंड बिकॉज ऑफ दिस रीजन दे हैव एब्नॉर्मली लो मेल्टिंग एंड बॉइलिंग पॉइंट. Clear? So as we move from left to right in a period, what happened? Melting and boiling point first increases and then decreases. But the melting and boiling point of manganese and technetium is abnormally less due to a very stable configuration. They don't do the delocalization of the electron, and because they don't delocalize their electron, that's why they don't form metallic bond, and if they don't form metallic bond, then the melting and boiling point should be low. So melting and boiling point depends on the number of unpaired electron. When we move left to right, first number of unpaired electron increases, therefore melting and boiling point also increases, and then unpaired electron decreases, that's why it is also decreases. But in these cases, because of very stable configuration, there is no delocalization of electron, and because of no delocalization of electron, no bond formation is there, less metallic bond formation tendency is there. That's why abnormally low melting and boiling point. Abnormally low melting and boiling point. Now, when we move from first to second, second to third transition series, melting point and boiling point increases. Means when we move down the group, melting point and boiling point increases. When we move down the group, melting and boiling point increases. Now, what is the reason behind this? If we talk about the atomic size, on moving down the group, on moving first to second transition series, what happens? Atomic size increases. Due to the increase in the atomic size, ionization energy decreases. Now, due to the decrease in the ionic size, the tendency to form the metallic bond increases. It means when we move down the group, what happened? Atomic size increases. Due to the increase in the atomic size, ionization enthalpy decreases, and due to the decrease in the ionization enthalpy, tendency to form metallic bond increases. And if the tendency to form metallic bond increases, therefore melting and boiling point also increases. And because of this reason, tungsten has the highest melting point. Clear? So when we move up to down, means first to second, second to third, then what happened? There is a slight increase in the atomic size, due to which there is a decrease in the ionization enthalpy, and due to decrease in ionization enthalpy, tendency to form metallic bond increases, and due to the increase in the tendency to form metallic bond, they show more metallic character, and melting and boiling point increases. So this is all about the melting and the boiling point of the D block elements. So students, that's all for today. I'll see you in my next video with the other properties of the D block element.